Inverse trigonometric functions, integration. Here there are three forms that we use, integrals involving inverse trigonometric functions. Here the first, the integral of du over the square root of a squared minus u squared is sine inverse of u over a plus c. The second, the integral of du over a squared plus u squared is 1 over a tan inverse u over a plus c. Then the third one, which is somewhat tricky, I guess all three would be without having a clear understanding of how to actually form them. In Calculus 2, we will spend time talking about integration using trig substitution, and in that, basically, we prove why these are the case, and so you don't have to memorize these formulas. Once we get there, we will actually work through to produce the formulas using our calculus. So this third one, the integral of du over u times the square root of u squared minus a squared is 1 over a secant inverse absolute value of u over a plus c. Some of these integrals you have to complete the square. Some you have to separate the quotients, which does come up. And then some you have to use a very tricky u du substitution. Let's see. So for this one, this is straightforward from the sine inverse here, where a is equal to 3 and u is equal to x. And so if that's the case, then we have sine inverse of x over 3 plus c. The next is straightforward again, here where a is equal to 2 and then u is x minus 3. So this picks up the tan inverse. So the tan inverse involved the 1 over a on the outside of 1/2 times tan inverse of x minus 3 over 2 plus some constant. Well, what about this one? Well, here, let u equal to x squared. And so du is 2x dx. Well, if this is the case, then what we have here is the integral. Now the du is 1/2 du is the x dx. So notice here that the 1/2 and the du would give us an x dx. Well, I don't have an x in our numerator, but if we manipulate this u, I think we can get something. This is 1 over here u times the square root of u squared minus 2 squared, and this is du. So let's see, the 1/2 du, I'm just going to just write what we have again. This 1/2 du represents the x dx. Let's just write that. This is x dx. And this is all over the u. Here is our x squared times the square root of the u, which is x squared to be squared, minus 4. So here, this does give us dx over, this is x times the square root of x to the fourth minus 4. So the problem is good in our substitution. So where we started from, the substitution, we're able to get back to that exactly. So I start now again with the 1/2. The integral of 1 over u times the square root of u squared minus 2 squared du. Now, you note here that the a is equal to 2 and our u is x squared. So we write our answer. This is the 1/2 from here. For that secant inverse, you got to have 1 over a on the outside. Well, a is 2. This is times secant inverse of the absolute value of u. But u is x squared, so x squared is already positive, so no need for the absolute value. That's redundant. Divided by a, which is 2, plus constant. And this gives us, for our answer, you can simplify that to 1/4 secant inverse of x squared over 2 plus c. Now this one's interesting. Notice that there's a similarity between the tangent x and the secant square x. They are similar or connected by a derivative. So let u equal to tan x. So du picks up that numerator, secant square secant square x dx. So if we write this out, this is the integral of, I'm going to say that's just 1. It's going to be times du, which the du gives us the secant square x dx. Downstairs, this is the square root of 5 squared minus u squared du. Well, if it's the square downstairs in our denominator, if it's the square root of a number squared, a squared minus u squared, then that picks up the sine inverse, and this is u, which is tangent x divided by a. So here this is sine inverse of u, which is tangent x divided by a, which is 5, plus our constant. Let's look here. Simplify this by writing this integral into two integrals. So this is the integral of x over x squared plus 1 dx minus 3 times the integral of 1 over x squared plus 1 dx. The first one, we can use here a u du substitution. Let u equal to x squared plus 1. And so du is 2x dx. Well, 1/2 du picks up x dx, and that's our numerator. The second integral is the tangent inverse directly. So we have here 1/2 times the integral of 1 over u du. So the 1/2 du picks up the x dx, our numerator, and then the u downstairs is x squared plus 1. This is minus 3 times tan inverse here of x divided by 1 plus a constant. You can clean all this up. This is 1/2 times the integral of the absolute value of x squared plus 1 this is minus 3 times the tan inverse of x plus some constant. All right, let's see. Well, this one is tricky. We need to connect this tricky part, the square root of x, with this x here. Let's see. I know that the square root of x to be squared gives me x, so let u equal to the square root of x. I'm going to square both sides, so we get u squared is equal to x. And the reason why I do that is because taking the derivative of u and then the square root of x won't give me anything valuable to be able to simplify this integral that I'm given. So here, let's take the derivative on u squared equal to u. So this is 2u times du is equal to dx. But notice here that 2 du is interesting. This is dx over u, right? But u is the square root of x. Well, that's what we want. And u squared is equal to x. So if you think about it, here we have that 2 sitting there. This is 1. And then downstairs, we just have the square root of 1 minus u squared, and this is du. Now, does that make sense? It does. 2 du is dx over the square root of x. And so we have left 1 over the square root of 1 minus here x, but x is u squared. So we got it. So this is 2. Isn't this sine inverse 2 times sine inverse here of the u over 1 plus c? You simplify that. This is 2 times sine inverse. The u here is the square root of x plus c. Now, that was interesting. You took my sins and put them in a bag. The book of Job, chapter 14, verse 17, if I'm correct. I have to go back and check that. Complete the square on this guy. This denominator is begging me to have a perfect square trinomial. What other way in terms of how you would simplify this? So it's the integral from 0 to 2, 1 over, this is x squared minus 2x. Complete the square on this negative 2x. Take half of negative 2, we get negative 1. We square it, so we get 1. So we're going to add 1 and subtract 1. This is plus 2, that's given already. And then dx. This is the integral from 0 to 2. This is 1 all over. Now, these 3 terms here becomes x minus 1 to be squared. And this is plus 1 squared, right? Or just 1 dx. Just so you can see that this is actually tangent. So we get tan inverse of, this is x minus 1 divided by 1, right? Which is just x minus 1. And this is evaluated from 0 to 2. So we get tan inverse of 2 minus 1 minus tan inverse of 0 minus 1. So this is tan inverse of 1 minus tan inverse of negative 1. All right. We use what we know about the inverse property. So if tan inverse of 1 is equal to theta, then tan theta is equal to 1. And that implies, you know, that theta here would be pi over 4. That's the first one. What about this tan inverse of negative 1? Let's look at that statement. So here, if tan inverse of negative 1 is equal to theta, then tan theta equal to negative 1. This implies that here, theta is negative pi over 4. So if that be the case, then our answer, let's put this in a box. Crap, didn't want to go through the 0. So here we have tan inverse of 1, which is pi over 4. This is minus a negative pi over 4. And so we get pi over 4 plus pi over 4, and that gives us pi over 2. Or maybe a happy face with a nose. I don't know. Anyway, it's pi over 2. Okay. What is this? I don't know. I have an old deacon that said that he heard a sermon, and in the sermon, the preacher said that in life, there will always, for us, there will always be an opportunity. From the opportunity, always there will exist problems. And from the problems, there will come about in some type of way a solution. And from the solution, therein would lie other opportunities. And from those opportunities, problems will arise. And from those problems, solutions. And from those solutions, opportunities. And well, you get it. Just keeps on going around. Well, herein for this problem lies the problem, right? What is it? Okay. Well, let's see if we can simplify it. It looks like we need to complete the square, but we don't have all of what we need, right? Because typically in completing the square, you want to be able to form something like some x squared, let's say here plus, and not x squared. A squared plus 2ab plus b squared. I want to form something like that to be able to produce some a plus b to be squared. And this could be plus or negative, plus or minus, right? So we need to build what we want. So this is the integral of 1 over the square root. The first thing I'm going to do is to factor out a negative from within. I'm not taking a negative outside of the square root. That's impossible for real values, right? So now I'm going to complete the square on that 4. It's the integral of 1 over here the square root of negative x squared plus 4x. Take half of 4, we get 2. We square it, so we add a 4 and subtract a 4 right where we are. Take the negative part out. Take the negative part out. The negative 4 times this negative, we have a positive 4 on the outside of the parentheses, but still within the square root. So this is the square root. This negative 4 times negative On the outside, the -1 becomes a +4. This is minus, I have a perfect square trinomial. This is x plus 2 to be squared. This is dx. So this is the integral of 1 over the square root of 2 squared minus parentheses x plus 2 to be squared dx. Do you see that this matches up with the sign? Go back and look at it. The integral of du divided by the square root of a squared minus u squared. If it's u squared minus a squared, then we look for u on the outside to be able to form the secant inverse. So here this is sine inverse. Whew, what was that? And so we have sine inverse of the u, which is x plus 2, all over a, which is 2. This is plus c. Thank you. I think that will do it for now.